Welcome to experiment number 5. This is one of our more important experiments. In fact, well, they're all important and they're all, I think fun because circuits are just interesting and fun. They're like little puzzles that you put together and take apart. But experiment number 5 is important because in the lecture courses, you'll have to be able to manipulate and simplify and analyze circuits, combination, series, and parallel circuits. And this gives you a nice hands-on access to those circuits. And then also in the midterm and or final for the practicals, you might have to actually create and analyze a circuit in series, parallel, or combination. So the hands-on experience you get in this lab will be very important for both the lab and for the lecture. So first of all, for resistors in series, they look like this. There's one after the other. Now, the way that you can tell if resistors are in series is to look for junctions. And if there are no junctions, then that means that they are in series. And a junction occurs, where you have a wire that splits into two or more separate wires. So notice here, as I follow along this circuit, that there are no junctions along the way. Even if I were to draw this circuit in a slightly different way, like this, those two resistors look to be in parallel, but if I look at it more closely and I follow along through the circuit, I see that there are no junctions, so they are not in parallel. And sometimes we'll apply that in more complex circuits to just small portions of that circuit. Now, for resistors in series, there are several rules. First of all, resistors in series have the same current. And if you remember the rules that we have for capacitors in the lecture, remember they have the same current and they have the same current as the equivalent resistance. So whatever current is through the equivalent resistance is also through each of the individual resistors that make up the each of the individual resistors that make up the equivalent resistor. So imagine if I have a current flowing through here, it should probably follow for you that that same current will flow through each of these resistors. And we had a similar thing for capacitors in parallel, that they had the same charge, but the physical reasoning was different. Okay, so the first thing is that they have the same current. That's equation 1 in your lab manual. The second thing, I'm going to go out of order just a bit, is that the equivalent resistance is equal to R1 plus R2 plus ... however many resistors you have. So for example, in this circuit that I have, let me erase this. In this circuit, the equivalent resistance would be 2 plus 4 are 6 ohms. So 6 ohms and 12 volts. So the equivalent resistance is just the sum, 2 plus 4 equals 6, the sum of the individual resistors. The third, I like to use this for Ohm's law, V equals IR. And then finally the fourth is that the voltage across the source, or we call it the total voltage in the lab manual, I like to think of it as the equivalent voltage, or the voltage across the equivalent resistor, is equal to the sum of the individual resistors. So if I call this V1, I call this V2, and this is V total or V equivalent, then those two voltages have to add up to equal to the sum. And we had that exact same thing in the capacitors, same rule. In fact, these rules are similar, except notice that the equivalent resistance for resistors in series looks like the equivalent capacitance for capacitors in parallel. That is, the form is the same, that it's a sum, not the sum of the inverses, the inverse of the sum of the inverses. Also, I just want to point out that this, later when we get to multi-loop circuits, that this will be called the loop rule. We're not calling it that right now, I don't know, we're just not. Okay, so to apply these rules to this circuit, I would first find the equivalent resistance right here, and then I would say, well, the current through that equivalent resistance is V over R, that's 12 volts over 6 ohms. That's equal to 2 amps. That tells me that this current is 2 amps going through each of those. And then if I want to solve for V1, I could say V1 is I1 R1. That is going to be 2 amps times 2 ohms, which is 4 volts. And then V2 is I2 R2, which is 2 amps. In fact, I1 is equal to I2, so I could just drop the subscripts, times 4 ohms. and that's going to be 8 volts. And then I can do a quick check and just see that 8 plus 4 is equal to 12, as it should be, because I have a total of 12 volts across these two capacitors. They split up that voltage, and I also have that 12 volts across the equivalent capacitance. So if I want to think about this V total, I could say V equivalent. That might help you to think about it better when we get into more complex circuits. I also just want to point out here that if I have 8 volts, 4 volts here and 8 volts here. And remember, with capacitors, we said that bigger capacitors have smaller voltages. That's not true for resistors. For resistors, the analog doesn't true. The analogy doesn't hold true. It's completely different, resistors and capacitors, but a lot of the rules are the same. For resistors, a bigger resistor will have a bigger voltage because they have the same current. So if I increase my resistance, I increase my voltage. And so notice here that I have the bigger voltage across the bigger resistor and the smaller voltage across the smaller resistor. So if I increase my resistance, that increases also my voltage. Okay, so those are resistors in series. Let me show you how they would look in the lab if you're hooking up resistors in series. So this would be your power supply. All right, I'll call this red and black. And I'm going to have my first resistor right here. Now remember, you have these little boards, they have these 4 terminals, and then you have these sort of connection terminals. So I'm going to hook it up right there, and I'm going to have a resistor right there. And then I'm going to go here, I'm going to go to my next board. And let's say on this board I actually have 2 resistors. I hook it up like that, like we did before. And then this goes right here. And then this wire goes back to our power supply. And then if I want to measure the current in any one of these, I put an ammeter in series with those resistors. I can place it anywhere. I could place it here. I could place it here. Of course, those should all measure the same current. And then if I want to know the the voltage across any one of these, then I could place a voltmeter here, or I could place a voltmeter here. Or if I want to know the voltage across the power supply, I could place a voltmeter here. Remember, voltmeters are in parallel, ammeters are in series. Let's look at parallel resistors. Let me begin first by giving you the rules. So for resistors in parallel, they have the same voltage. Resistors in series have the same current. These have the same voltage. And, as we said before, they have the same voltage as their equivalent resistance. Okay? And then also, next, is that the equivalent resistance is equal to 1 over R1 plus 1 over R2, etc., however many resistors you have. Just remember, this looks like in form the capacitance for capacitors in series, although this is resistors in parallel. So those two equivalent formulae, those 4 equivalent formulae, it's like they're all swapped. The forms of them are. Okay. Third, we're going to use Ohm's law right here to fill in our third place. And then fourth is that the current is equal to, the total current is equal to I1 plus I2. Or in your lab manual, we call this IA is equal to I1 plus I2 is equal to IB. Let me show you what that means. So if I have, say, a current of 8 amps, and then I break into 2 sections, and here I have 5 amps, then what is this current? Well, I would say that 8 is equal to 5 plus I, and so I then is equal to 3 amps. This is called, by the way, the junction rule, and we'll use this for multi-loop circuits. Now, in this case, let's say that this is my IA, and this is IB, then this would be I1, and this would be I2. The sum I1 plus I2 should equal either IA or IB, and of course IA will equal to IB. Okay, so you can write it that way, or in class we will write it I-tot is equal to I1 plus I2 plus however many junctions we have, however many wires. I do want to say that that really this occurs, we apply this junction rule at a junction, and a junction is where two or more wires combine. Okay, so let's try to do this one. Resistors in parallel are quite a bit easier to do because resistors in parallel have the same voltage. So whatever voltage I have here, I will also have here 12 volts, and I'll also have here 12 volts. Then if I want to calculate I1 is going to be, well, V over R, right? Solve this for I. V over R are 12 volts over 6 ohms. That's equal to 2 amps. And here, I2 is going to be 12 volts over 3 ohms, and that's equal to 4 amps. So those are my currents I1 and I2. Now I can also figure out what is the equivalent of this circuit. Well, if you're in my class, you know the 6 and 3 is a combination that I like to use because it just works out easily. 1 over a 6 plus a third is equal to 2 ohms. So the equivalent of this resistor is equal to 2 ohms. Now, if I want to know that current, I have 12 volts over 2 ohms, then that current is equal to 12 divided by 2, or 6 amps. So I have a total of 6 amps. That 6 amps is going to be IA, and it's going to be IB, 6 amps and 6 amps. And then also notice that that I tote, which should be equal to I1 plus I2. And we can check to see if that's the case. Is it? Well, I had 6 amps, I1 was 2 amps, I2 better be 4 amps, and it is. So that checks out. When you're going through and doing these circuits, you should always run these little checks to make sure that everything is okay. Let's look at what this might look like in the lab, and I'll show you in a separate video. But in the lab, you can hook this up in 2 different ways. Let me show you first of all the way not to do it, just because it's cumbersome. So I have a power supply, and then here's my resistor board. I'm not going to draw the resistor on it. I can hook it up to that power supply. And then I can take another resistor board. You get the idea. I should have 2 more circles. And I can hook it up to that power supply. Don't do it this way because then you get a whole bunch of wires over here on your terminals of your power supply, and it's cumbersome to do it that way. However, I like showing it this way because it realizes the fact that whatever voltage I have here, I also have here and here. These resistors are independent of one another. That they have they'll have the same voltage, and it doesn't matter if this resistor is big or small, or this resistor is big or small, that they'll always have the same voltage. That's why our homes are always hooked up in parallel. That way every electrical device in our home has the same voltage of 120 volts. No, so don't do it this way. Instead, you're going to hook it up this way. Think about it in this way, but hook it up in this way. So here's your power supply. This is the exact same technique, or ended result. There's our board. Actually, you're going to connect it to these terminals, of course. And then I'm going to have another board up here. And I'm going to run wires from here up to here. And then if I have another resistor, I run another set of wires, and on and on. So that's the best way to hook up these resistors in parallel. And I'll show you that in a separate video with the actual devices. Now let's look at combinations. So first of all, let me just rewrite the rules. So for series and parallel, these are our rules. Series have the same current. And they have the same current as the equivalent resistor. Oop, that's not a 2. Have the same voltage. And they have the same voltage as the equivalent resistor. That's just sort of like an extra little thought you have. The second is the equivalent. All right, and remember these are flip-flopped from how we saw those same forms for capacitors. The third is just Ohm's law. Those are the same. And then fourth, for series, we have so we have the loop rule. V equals V1 plus V2. And I'm going to write this as V equivalent, though in your lab manual, I think it's written a little bit differently as like V total But V equivalent, it means the same, that whatever voltage is across the equivalent of those individual resistors will be the voltage, or will equal to the sum of the voltages across those individual resistors. And then here, and remember this is called the loop rule, and then here for number 4, I have what, I total, or IA, is equal to I1 is equal to I2 is equal to dot dot. I'm sorry, that's not it at all. I don't even know what I'm writing. Um, I was writing and not thinking. That's what I was doing. All right, I total is equal to I1 plus I2. Let's look at this circuit. Let's say that I have 12 volts right here. First of all, let's find the equivalent. To find the equivalent, I'm going to start with this section. This has an equivalent of 2 ohms. 1 over a third plus a 6 is 2. And then my final circuit will be 3 ohms. I said 2 plus 1, that's equal to 3. I have 12 volts right here. That means that I have a current of 4 amps. So I have 4 amps there. I get V over R, 12 over 3 is 4 amps. That means that I have 4 amps coming here, and then that 4 amps goes through this 1 ohm resistor. Now if I have a 1 ohm resistor with 4 amps, remember if I ever find 2 quantities, I can always find the third. So the voltage here is going to be 4 volts. Now if I have 4 volts here, and I have 12 volts here, that means across these resistors in parallel, I must have 8 volts. In fact, I know that the equivalent of that is 2 ohms, and so if I have 4 amps over 2 ohms, and that will give me 8 volts. Let me draw that picture. So if I have a 1 ohm and a 2 ohm, and I have 4 amps going through each. 4 times 1 is 4. 4 times 2 is 8. And of course, that's going to be an application of Rule 4, or excuse me, not Rule 4, an application of, yeah, Rule 4, that 4 plus 8 must equal to 12. All right? Now, if I have 8 volts there, that means I have 8 volts here and 8 volts here. Then I can find the current through each of those. This one will be V over R, 8/3 amps. And this one will be V over R, or 8/6 amps. That's 4/3. Then if I want to apply this rule, I can say, well, 8/3 plus 8/6, which of course simplified, is now 4/3. That's equal to 12/3, or 4 amps. Which is equal to the total current that I have coming into that circuit. So that's a combination circuit. Now, the way you set this up in the lab can be different, but you just want to make sure that you have the different elements there. So here's my power supply. I'm going to come first to the first resistor, where I come in and then I go out. And then I can do this in a couple of different ways. You could have 2 wires here. That might be the easier way. You get the idea. And then those 2 could come together and then come back to the power supply. Try to refrain from putting multiple wires onto the power supply. That would be in parallel, but I'll let you, that's probably not the best way, because then you have this sort of, you're collecting these 3 wires together in some way. I'm going to let you think about that and what are some other ways that you can hook this up so that so that you have that parallel branch in your circuit, but to use as few wires as possible. Please try to refrain from doing what I've done here, where you have 2 wires coming in and then connecting to a 3rd wire. I want you to think about that. It's certainly possible, and there are a couple different ways to do that. Okay, I think that is everything for this. Yeah, that's all. We'll have a separate for the practice.